You remember that big chart hanging on the wall in your high school chemistry class, right? The periodic table? Well, it turns out it's so much more than just a boring list of elements. Think of it like a map, a truly revolutionary guide to every single building block of our entire universe. It's the thing that took total chaos and turned it into beautiful, predictable order. And today, we're going to dive into its incredible story.
Hey, don't just take my word for it. A Nobel laureate, Glenn T. Seaborg, a guy who actually discovered several new elements himself, he put it perfectly. For him, the table was proof positive that the universe isn't just some random jumble of stuff. Nope, it shows there's a deep underlying order, almost like a family resemblance between the elements, and it's the key to understanding, well, everything. All right, so here's our game plan. First, we'll see what things were like when chemistry was total chaos. Then, we'll join the hunt for a pattern. After that, we get to the big one, Mendeleev's genius prediction. We'll look at a fundamental upgrade that changed everything, decode the table's hidden logic, and finally, see how we can use it to unlock some amazing periodic trends.
Okay, let's hop in our time machine and head back to the 19th century. Now, this was a super exciting time for science, right? But for chemists, well, for them, it was kind of like trying to drink from a fire hose, a serious case of information overload. New discoveries were just pouring in, and the whole world of chemistry was, to put it mildly, a complete and utter mess.
I mean, think about it. At the start of the 1800s, things felt pretty manageable. Scientists only knew about 31 elements. You know, the big ones like gold, iron, oxygen. You could probably keep track of all of them and their quirky little personalities without too much trouble.
But then, bam! Fast forward just 65 years, and that number more than doubles to 63. New elements are being found left and right at this dizzying pace, and each one has its own unique set of properties. It's kind of like someone handed you a deck of cards, but with no suits, no numbers, no colors, just a random pile of faces. That's exactly what chemists were up against. They were desperate to figure out the rules of the game.
So, all this chaos kicked off what was basically a massive scientific detective story. The mission, if they chose to accept it, was to find the secret code, the hidden rule that governed all the elements. And you know what? Some of the early pioneers started finding some really interesting clues.
Okay, so one of the first big breaks came way back in 1829 from a German chemist, Johann Dobereiner. He started noticing these little groups of three, these families of elements that seemed to belong together. He called them triads. And what he found was wild. The atomic weight of the middle element, take sodium here, was almost a perfect average of the other two. This was huge. It was the first real clue that maybe, just maybe, there was some kind of mathematical logic hiding in plain sight.
And then, the plot thickens. A few decades later, an English chemist named John Newlands takes a shot at it. He lines up the elements by their atomic weight and notices something amazing. The properties seem to repeat every eighth element, just like notes in a musical scale. So, naturally, he calls it the law of octaves. And it was a brilliant idea, but there was a catch. The music sounded great for the first couple of octaves with the lighter elements, but once he got past calcium, the whole harmony just fell apart. So close, yet so far.
So this detective story really needed a hero to crack the case. And it got one in a Russian chemist named Dmitry Mendeleev. Now, he was looking at all the same clues as everybody else, but he saw something that no one else did. And that, right there, was the breakthrough moment.
So in 1869, Mendeleev puts forward his periodic law. On the surface, the idea sounds simple enough, right? Just arrange the elements by their atomic weights, and you'll see their properties repeat in these predictable cycles, or periods. But here's the thing. Other people had kind of flirted with this idea before. What made Mendeleev's work so different was his absolute, unshakable confidence in his system, and, well, its sheer elegance.
And this is the part that sets him apart from everyone. This is his masterstroke. See, Mendeleev didn't just organize the elements that were already known. No, when his pattern told him an element should exist, but it hadn't been found yet, he did something incredibly audacious. He just left a blank space for it on his chart.
His most famous prediction was for a gap right below aluminum. He called the missing element Eka aluminum. And get this, he didn't just leave a blank space. He wrote down a full description predicting its properties with stunning accuracy, its weight, its density, even how it would react with oxygen. And then, just a few years later, an element called gallium was discovered, and its properties, a near-perfect match to his predictions. This was the smoking gun.
This proved his table wasn't just a clever filing system, it was tapping into a fundamental law of nature. So here you can see one of his early tables, and look, there are the gaps he so confidently left. He was so sure about his system that he was even willing to break his own main rule. Check this out. He put tellurium before iodine, even though tellurium is actually heavier. Why? Because he just knew, intuitively, that iodine's properties meant it belonged in the same family as chlorine. For Mendeleev, the beautiful pattern was way more important than sticking strictly to the numbers.
Now, Mendeleev's table was absolutely revolutionary, but it wasn't quite perfect. There was one last major plot twist left in our story. It would take another brilliant scientist to find that final, hidden piece of the puzzle, the key that would unlock the modern table we all use today. And the fix was so simple, yet so profound. You see, Mendeleev had organized everything by atomic weight, basically how heavy an atom is. But in 1913, a scientist named Henry Moseley figured out the real organizing principle. It wasn't weight at all. It was the atomic number, which is just the number of protons in an atom's core.
And this discovery gave us the modern periodic law. By simply reshuffling the deck and ordering the elements by their atomic number instead of their weight, all those little nagging problems in Mendeleev's table, like that whole tellurium-iodine thing, they just vanished. Poof, gone. The atomic number, it turned out, was the true fundamental code that Moseley had finally cracked.
All right, so now that we've cracked the real code, the atomic number, we can finally appreciate the beautiful, elegant logic behind that weird shape of the periodic table. Because believe me, it is not random at all.
This is where you see the true genius of the table's design. That strange shape? It's a map of an atom's structure. Seriously. Think of an atom like a high-rise building, and the electrons live on different floors or orbitals. The periodic table is basically the architect's blueprint for all those buildings. These different colored blocks you see, the S, P, D, and F blocks, they literally tell you which floor the atom's outermost, most important electron lives on. And since those outer electrons control pretty much everything an atom does, its address on this blueprint tells you its entire chemical personality.
And this is where the table goes from being a cool chart to an unbelievably powerful tool. Because the structure is so logical, you don't have to memorize a million facts about every single element. Nope. You can actually predict their properties just by seeing where they live on the map. Let's just take one quick example: atomic size.
Okay, check out the numbers for the elements in the second row, what we call period 2. As we go from lithium on the far left, all the way across to fluorine on the right, do you see that? Do you see the trend? The atoms are actually getting smaller. How weird is that?
So what's going on here? I mean, it seems totally backward, right? You're adding more stuff to the atom, so it should be getting bigger. But here's the trick. As you move across that row, you're also adding more protons to the nucleus in the center. That means the positive charge in the middle gets stronger and stronger, and it pulls all those surrounding electrons in just a little bit tighter. It's like a stronger magnet, shrinking the whole atom. It's a perfectly predictable pattern, and it works all across the table. It's not random chance, it's just pure physics.
So we went from a chaotic jumble of disconnected facts to this elegant, predictive map of all 118 known elements. The periodic table is, without a doubt, one of the greatest achievements in all of science. It brought order to our known universe. But it leaves us with this one tantalizing question. What happens next? What lies beyond element 118? What bizarre new properties and incredible patterns might emerge when we finally venture